Hello and welcome to lesson 2 in the alkenes topic. So this lesson largely builds on what's in lesson 1, particularly the focus on geometric isomerism and spotting geometric isomerism and naming more complex geometric isomers according to a set of rules called the CIP rules. Okay, so we've got some starter questions. All right. For the first part, pent-1-ene needs to be represented 5 different ways using the displayed formula, molecular formula, empirical formula, structural formula, and skeletal formula. Then we have a name and outline the mechanism question. So this is a name the mechanism and draw the curly arrow mechanism question following the instructions that are given. So pause the video and have a go at those tasks. Okay, so we should have some answers. Might not be sure about the mech, but we should have had a go. So there are 5 different representations of pent-1-ene. We've got a displayed formula, molecular formula, empirical formula, structural formula, and skeletal formula. I'm not going to draw out all the possibilities here, but I will point out that obviously if you've got the double bond over on the right-hand side of the molecule, that's absolutely fine because it's still carbon 1, right? As long as everything else is correct, okay? I chose to have it on the left for this section. So then for the mech, after you've checked your answers, it's elimination. The hydroxide ion from the hot ethanolic, whatever it was, potassium hydroxide, is acting as a base. So we have 3 curly arrows, a cascade of electron pair movements, okay, resulting in formation of a double bond and removal of the chlorine, as well as the products being shown, pent-1-ene, and the byproduct of water and the chloride ion being shown. So I'm just going to kind of remind you about a couple of things. The first one is, remember that when the hydrogen gets taken away by the hydroxide ion, which is acting as a proton acceptor, it's being removed as H+. It is taking nothing with it, right? It's not taking its electron with it, which means that the pair of electrons that's highlighted here, okay, then moves, you can imagine it almost swivels 90 degrees up and it forms the double bond between the 2 carbon atoms. At the same time, we get the removal of the chlorine, and because it takes a pair of electrons with it, it leaves as a chloride ion, okay, because it now has 1 extra electron that it didn't contribute originally. So just a reminder about mechanisms and the idea that these pairs of electrons moving around often results in the formation of positive ions or negative ions, okay? But you need to think about the direction of that movement. If the electrons are being taken away like they are from the hydrogen, then that's going to make a positive. If they're being sort of, taken with, as they are with the chlorine, that's going to make a negative ion, okay? So obviously that mechanism is actually from the halogenoalkanes topic, but it's 100% relevant here because it has made the alkene that we were looking at in the first half of this task. Okay, so thinking about more complicated geometric isomers. Last time we looked at the idea that you can designate molecules as E or Z if they have a certain combination of different functional groups or different elements attached to carbons either side of a double bond. Let's introduce this concept, right? Here's a molecule, 1 bromo, 2 chloro, 1 fluoroethene, okay? This thing does have geometric isomers, right? It does exhibit geometric isomerism, but there's a problem. And what you should be able to do is look at that, and even if it's vague or inelegant, you should be able to sort of verbalize out loud what the issue is. So when I've been teaching this lesson, various answers have included things like they're both on the same side, or, things like there are 3 different atoms, or, there isn't a hydrogen on the left-hand side. And all of these are rough verbalizations of the issue. And the issue is, how do we designate E or Z? It might be okay on the right-hand side because, okay, we're going to say we move from the chlorine. So just to highlight, right, and we go across the double bond. But then there's kind of a fork in the road. Do we go upwards to bromine or downwards to fluorine? Is it E with respect to the fluorine, or is it Z, right, using the bromine as the guide? And there's a rule that we use to sort of decide this, and that's what we're going to learn about. Just to explain further why this is an issue, if we were to change this structure slightly, if I'd shown you that, the thing that's in blue, then you'd probably guess correctly that it was Z, right? If instead I'd shown you that, right, you probably would have guessed correctly that it was E. And that's because the examples we looked at so far were all like that, where there was really just two hydrogens either side of the double bond and then two other things, okay? But the problem we have this time is there isn't a hydrogen on the left, there's two halogens, and how do we compare them? So, as usual, there's kind of a set of rules for this, right? It's called the Kahn-Ingold-Prelog rules for naming. And this goes a little further when you study undergraduate chemistry, right? But this is the kind of potted A-level version. Pause the video and copy down those rules, and then we'll think about how we're going to use them. Okay, so if you've got a copy of these in front of you, it says locate the double bond and look at the left-hand side, right? It doesn't have to be the left-hand side, but that's just a convention to sort of start on the left-hand side. So here it is, right? We've got the molecule, locate the double bond, look at the left-hand side. So we're looking at the left-hand side, we've got fluorine and bromine, and we've already established that that's a problem, but now we have a method to solve it, right? Compare atomic numbers and assign priority to the higher one. So there's a new phrase, priority, right? So we're doing a comparison of atomic number, okay? So what we'd need to do is use a periodic table. The two elements that we're doing a comparison on are fluorine and bromine. They're both halogens, so they're in the same group, group 7. Fluorine has an atomic number of 9, and bromine has an atomic number of 35. So let's think about those numbers. We don't have to mark them on. I'm just doing it for this example. What that means is bromine has priority. And when we've assigned priority, what that means is that's the thing we're using as our guide in terms of the geometry, right? So now we actually have the answer, but let's go through the remainder of the steps anyway, okay? We're saying that we're tracing a line that way. See the orange highlighting? It's basically saying, well, bromine's our guide because it's got the higher atomic number. It's the higher priority group or atom. Look at the right-hand side and assign priority there. So we do the same kind of thing, right? Now, in this case, actually, most of the time you don't need to check the periodic table because if you're comparing anything with hydrogen, then the thing that's not hydrogen is always going to win. And the reason for that is hydrogen has an atomic number of 1. So any other element will have higher priority than hydrogen, which makes it fairly straightforward. But just to be clear, the number for chlorine is 17, right? So even just looking at the raw numbers, chlorine wins. Because chlorine wins, that means we've got an indication of our geometry. They are on the same side, they are together. So this is Z, 1 bromo, 2 chloro, 1 fluoro, ethene. That's its full name. Okay. So we've now got a method we've designated as E or Z as appropriate. Best thing for you to do is to try and put this into practice. Okay. So let me move that out of the way. There we go. There are 6 examples, getting progressively more complex. The 6th one is very sort of tricky. I'll talk through that one afterwards, but have a go at, what you can, all right, using the CIP rules that we've just established. Pause the video and try and designate each of these as E or Z. Okay, so it may be that you struggled with maybe 5 or 6. Hopefully you getting there okay between 1, 2, 3, up to 4 or so. All right. Here's the answers. ZZ, that's how that reads, ZZ. Okay. I'll explain a couple of these, although I'm not going to do them all in full. All right. Hopefully the first few are relatively straightforward. So let's have a look at number 4. So the answer is that it's Z, okay? The left-hand side, hopefully, will be relatively straightforward, right? As I've said before, if you're doing a comparison with hydrogen, the thing that's not hydrogen is going to win. But very specifically, it's the carbon atom that's being compared with that hydrogen atom, okay? Carbon has an atomic number of 6, hydrogen is 1, so carbon has priority. So we know that we're going that way. And then we head over here, and then we have to decide what we're doing, okay? So we know that the answer is Z, which actually means it must be that we're going downwards, right? But let's explain why. Well, when you do this, right, you compare the carbon here and the carbon there, they're actually the same. But at that stage, what you have to do is look at what's attached to that carbon atom, okay? And what we've got is 3 hydrogens in the top section and 2 hydrogens and an oxygen in the bottom section. So it helps a little bit if you have actually drawn out the DF sometimes, okay? What we're comparing is that lot versus that lot, okay? The big discriminating factor here is the combined atomic numbers of the carbon and the 3 hydrogens. That's like 9, 6 plus 1 plus 1 plus 1. When you've got the oxygen, that has an atomic number of 8. So as soon as you put that in, that makes the lower section the higher priority group. So let's tidy up. Now, it might be that you struggled with that, but now that I've explained number 4, right, you might be able to get your head around 5 at least. All right, and I'm not going to explain 5 because it's a very similar logic, right? 5 is E because we trace a line like that. The right-hand side of number 5 is the same as the right-hand side of number 4, okay? The left-hand side's different, but the right-hand side is the same. So I will explain number 6 because, again, there's a bit of a kind of trick to this. It is tricky. It's not something you usually have to do for A-level chemistry. It's on the sort of challenge side of things. Let's just tidy up here. So for number 6, okay, what we wind up with is an E isomer, but we need to be able to explain why, okay? So let's look at the left-hand side, right? On the left-hand side, we've got that carbon versus that carbon. And again, it helps a little bit if you expand the structure, okay? That first carbon, right, what we're looking at is that. And then the first carbon underneath, what we're looking at is that, right? That's kind of what we're looking at if we just go 1 bond deep on each of them, okay? So again, what we're thinking about is what's attached to this? That's 8. What's attached to this? That's 6. Okay, the winner is the top one because it has the oxygen atom attached, which has a higher atomic number. So that bit's actually okay-ish, right? Again, you're just getting up and running with these. And so some of the ones towards the end of this task were a bit tricky. This one is where things get, you know, definitely on the harder side. You could be easily forgiven for picking this section. And the reason you could be easily forgiven for that is it looks bigger. It looks like a big, bulkier group, right? It looks like something that should have higher priority. But because of the way that this works, there's an additional rule, which you don't need to know for A-level, but I'm going to tell you anyway. It's called the first point of difference rule, right? So remember what we've been doing so far. If we kind of expand this structure, the first one that we're looking at, that carbon, corresponding colours shown, looks like that. If we do the same thing here, then what we get is that. So what that means is we're doing a comparison of 17 versus a comparison of 6. And yes, there is another chlorine over here, but actually that's irrelevant because it's not directly attached to this carbon, which is where we're doing the first comparison. Okay, so that means that the winner is the lower section, and we can finish off our kind of trace line, and that's why we arrive at E as our designation. Obviously, this starts to get quite complicated with larger molecules. Fortunately, most of the time your E and Z designation is pretty straightforward in A-level, but there's no reason why they couldn't throw a sort of more challenging question at you. I doubt it would be approach the level of number 6. It'd probably be more like 4 or 5. Okay, so let's move along. A little comment on boiling points. Okay, back to this. Because when we first looked at boiling points of alkenes, we hadn't considered E or Z. There is a slight difference here, okay? So remember, alkenes, the strongest intermolecular force that acts on them is the van der Waals force. And we said that size is, usually the most important thing that governs the strength of van der Waals force. But how does it work when you're comparing molecules that have the same number of electrons, right, but have a different spatial arrangement of atoms, like geometric isomers do? So if we look at the skeletal formulae for Z-hex-3-ene and E-hex-3-ene, they look like that. So remember, it's the same structural formula, same number of electrons, same chain length, right? But because of the geometry, there's this slight difference, in how the directions point away of the things that are attached to the double bond, and actually that has a slight impact. The easiest way of thinking about this is it's a lot like the comparison between straight chain alkanes and branched alkanes. So just to remind you about that, this isn't going in the notes or anything, but if you were to compare pentane with methyl butane, this is something that quite commonly comes up in the alkanes topic, right? In the case of alkanes, branched alkanes always have lower boiling points than straight chain alkanes, even if they've got the same number of electrons, like these two things would do. So the logic here is the same, right? If you're comparing the boiling points of these, what you're really looking at is how closely the molecules can pack together. And if they fit nice and snugly, right, because there are no branches, like in this case over here, you're going to get a higher boiling point because you've got more kind of surface area. Closer packing is the phrase we use. The same logic can be applied to E and Z isomers, right? So if we take our Z isomer, looks like that, but really what we want to think about is how closely does it pack with another Z isomer, because that's really what we're thinking about, is the intermolecular force between molecules that are the same. And then if we do the same thing with the E isomer, okay? Get a bit messy here, apologies. Okay, let's just sort that bit out. Because the Z isomer has this better complementary shape almost, you get closer packing, right? Z isomers tend to have slightly higher boiling points. Okay, because you've got closer packing and stronger van der Waals forces between molecules of Z-hex-3-ene than you'll get between E-hex-3-ene. It's probably not a major difference. I haven't checked the data, but it's probably not a huge difference because they are still the same size, but you will get this slight difference. Okay, so remember the phrasing that we use here is, we would say that Z isomers get closer packing, and therefore you get a stronger van der Waals force. Just a little aside, this is actually the same reason, essentially, why certain oils are liquids at room temperature, but other very much related, compounds that you find in what we call fats are solids at room temperature. It has a lot to do with orientation around double bonds. And if you've ever studied any food science, you've probably heard of the terms saturated and unsaturated fats, right? Or trans fats, which basically refers to the E form, right? Not quite the same thing, but very, very similar. actually it's to do with their physical properties and things like the fact that the certain fats harden a bit more easily, right? And there are kind of, health disadvantages to various things and bits and bobs. But the next time you've got some vegetable oil versus some butter in front of you, to some degree, what you're looking at is the difference between molecules that have lots of Z double bonds and molecules that have more E double bonds, or some molecules that have no double bonds. So, little comment on boiling points. Last bit of this lesson is actually kind of a, again, a bit of a tangent, right? Drawing in some stuff from the alkanes topic. So some facts about alkenes: you can burn them, right? They burn with a yellow smoky flame. In other words, they're not very, very useful as fuels, right? They tend to burn quite incompletely. They tend to combust incompletely rather than completely, okay? You don't need to know why, but they do, okay? So they're not useful as fuels. They're also far more useful to turn into polymers, plastics, things like polyalkenes, polyethylene. But just a reminder, you can burn them. They will burn. They will react exothermically with oxygen. So a bit of practice recapping on simple equations for combustion reactions, and then we're done. So pause the video and have a go at writing these equations. Okay, so what you should have is a molecular formula plus oxygen goes to the relevant combustion products. So for number one, there's really only one answer, right? And it looks like that, and that's how it balances. For number two and number three, I didn't specify whether your incomplete combustion was going to produce carbon monoxide or carbon particulates, or actually sometimes you can see them written as a mixture where it's both CO and C produced. But what I've done is I've provided two alternatives for number two and two alternatives for number three. Okay, that draws lesson 2 to a close.